All right, so this is problem number 4, MCQ from the progress check. It's a little harder than what I would normally give you on a test or a quiz, so don't stress out if you don't understand it, but for those of you who really want to learn and kind of see where these are coming from, I'm gonna walk you through this video. First of all, when we have done this problem before, we have always, let's say I took a piece of charge here, it goes out of the positive and then down into the left. We used this angle as theta. The angle that the sine comes from is when we use the angle from the vertical rather than from the horizontal. And you can see that when we start with a piece of charge here, the angle that it makes with the vertical is 0. And then as you move your way all the way around to the top part, then the angle goes from 0 all the way to 180 or pi. So that's where the values are coming from. Another way to think about it, though, is if you were to solve this using cosine, cosine looks like this. And if I went from, and I know this is not beautiful, but if I went from pi over 2 to negative pi over 2, which is where we take our pieces of charge at pi over 2 and negative pi over 2, you can see that the graph itself is a hump in the positive side of my x-axis. If I were to look at a sine graph, the sine graph is going to start at 0, work its way down, and you can see that that same graph that makes that positive concave down sort of hump is from the limits of 0 to pi. So that's where we can kind of show that relationship of cosine from negative pi over 2 to pi over 2 is the same as sine from 0 to pi. Now let's kind of talk about how to solve this problem. So I'm going to erase all of this to clean it up. We can see that as we take pieces of charge from the symmetric sides of my electric field, electric charged ring, that the y components cancel out. And so when we do our integration, I need to include that x component. So cosine theta, because again, I'm going to use this guy as my theta, and then I can rewrite it as sine later. What you want to notice is that when I have an electric field from the positive charge, all of the y components cancel out, and I get a net field that points to the left. If I were to take a electric field from the bigger ring on the outside, it's further away. The equation's going to be the same, but it's going to be a smaller electric field because the electric field is inversely proportional to distance squared. And so that's why we know that the negative charged ring is going to have to subtract from the positively charged ring. And the net charge is going to point left in the end. So I'm just going to solve this as a general expression. I'm going to solve for the lowercase r first and then plug in the bigger 2r, or not the lowercase, but the single radius for the small circle r, and then plug in the 2r and subtract them later. But if we're solving this, I know that lambda is equal to dq over ds, and I know that ds is equal to r d theta, and I know that since dq and cosine theta are changing, it'll be easier to integrate if I solve for dq in terms of d theta. So that means I multiply the ds to the lambda, but the ds is also equal to r d theta, and this is going to be my new dq. I can also see that the r squared is a constant. It's R, big R, and so I can pull that out. Plug in my new dq, lambda, big R, d theta, cosine theta. And then from there, I can reduce. So k lambda over r, integral of cosine theta d theta, and I go from negative pi over 2 to pi over 2. Now, one thing I want you to keep in mind when you're doing this problem is you probably won't see the answer in the answer key, and that is because lambda is not an expression that was, or a variable that was given to you to use, and you don't see it anywhere in the answer key. And so what you want to do is make sure that you rewrite this, because there's uniform charge distribution, in terms of the full charge over the full arc length, which is pi r. And then when we plug that in, we get k q over pi r squared, because I plugged this guy into here. And then I've got the integral. Now I'm going to make my substitution, because we talked about it up here. My sine of theta from 0 to pi. Okay. This I know is going in the negative direction. I can even call that negative if I want, because electric fields are, sign is representative of direction when we're trying to do the sum of the electric field lines. I'm going to do the same thing, except I'm going to add the negative charge. It's the same equation, but this time I have double the radius, so I have to plug that in and square it, and the integral again is the same, from 0 to pi of sine theta. Now, everything basically cancels out here. I've got, or sorry, not cancels out, but factors out. I've got negative, or let's call it a positive, k q pi r squared. And this first bit is basically just copying that whole thing. And then the second bit is basically everything I pulled out, except for I've got a 1/4. When I square that denominator, I've got a positive 1/4 that's left over. And then from there I can see I get negative 3/4 kq over pi r squared, the integral from 0 to pi of sine theta. This is in the equation sheet as a positive value. Remember, this negative indicates the left direction, but most of the time I just take the absolute value, and I can see that that is B.